In this lecture, we will learn about new reactions of alkenes, and these reactions are epoxidation and dihydroxylation. Epoxidation leads to transforming an alkene into what's called an epoxide, and dihydroxylation leads to or is a transformation of an alkene into a diol. So let's begin with epoxidation. This is the general structure of alkenes. This is the general structure of alkenes. Alkenes can undergo epoxidation reactions if they react with peroxy acids like MCPBA. I will write the abbreviation and then of course the structure. So alkenes can react with peroxy agents to make what's called epoxides. So this epoxides are three-membered compounds that contain carbon-carbon bond and two carbon-oxygen double bond, two carbon-oxygen single bond. So this is an epoxide. Epoxide or oxyurane in heterocyclic chemistry. Epoxide, and that's if the alkene reacts with MCPBA. MCPBA, and M is small case, please pay attention to this. M is small case, CPBA are all capital letters, yeah? Okay, so the MCPBA, the structure for it is this, the following. It's meta-chloro, so a chloro group on position 3 with respect to a peroxybenzoic acid. So this is meta-chloro, this is the meta position, meta-chloroperoxybenzoic acid. So that's what this stands for. So meta-chloroperoxybenzoic acid. Oxidation reaction takes place and epoxide forms that contains 3 bonds, and one's carbon-carbon single and two carbon-oxygen also single bonds. And epoxide or oxyurane is formed in this case. Now, this is an example of an epoxidation reaction. If you take this alkene and then you react this with MCPBA, then this epoxide forms. This epoxide forms, and epoxides are very important in organic synthesis because they are strained molecules. They can undergo ring opening, what's called ring opening. That's because small rings have angle strain. They are susceptible to breakage. To relieve the strain, what may be called then ring opening reactions, which could be useful from a synthetic point of view. So this is an example. This is another example, but this time we take cyclohexene. If you take cyclohexene and we react this with MCPBA, then the corresponding epoxide forms. But the corresponding epoxides will have the epoxide on one side of the ring because, as you know, that rings have two sides, up, down, right and left. Okay, so the epoxide could be up like what is shown here. Yeah, so that's the structure of the epoxide. Well, it's already mentioned that epoxides are strained molecules, which means they can undergo ring opening reactions. Okay, if they are treated with suitable reagents, and the suitable reagent would be, like in this case, if this cyclic epoxide is treated with the hydronium ion. So if it's treated with the hydronium ion, like in this case, then a diol forms. We will work out a mechanism for this. This diol forms, and this diol, of course, a diol is a compound with hydroxyl groups on adjacent carbons. This is a trans diol. It's a trans 1,2 diol. So a trans 1,2 diol is obtained if the epoxide of cyclohexene undergoes ring opening with the hydronium ion. So this is a ring opening of the epoxide. The first step in this mechanism would be protonation with the hydronium ion. So this is the hydronium ion, H3O+, okay? Now, there are two, of course, there are two lone pairs on oxygen. Okay, the epoxide will be protonated. The epoxide will be protonated by the hydronium ion, and that hydrogen-oxygen bond breaks, releasing electrons to the positively charged oxygen. If that's the case, then this intermediate would be obtained. So a protonated epoxide. A proteinated epoxide is even more reactive than the original epoxide, and as you know, as you might predict, these two carbons here, or the two carbons that are bonded to oxygen in the epoxide ring, these two carbons are electrophilic. And they are electrophilic because of inductive effect. So there is inductive effect on that carbon and here. So plus delta here. These carbons are electrophilic. These are electrophilic carbons, that carbon and also this carbon here are both electrophilic. Nucleophiles can attack that. All those electrophilic sites are susceptible to nucleophilic attack. In this proteinated epoxide, these carbons are now made more electrophilic. That's because oxygen is now protonated. Oxygen has a positive charge. So this carbon, that carbon, and also that carbon are now more electrophilic, and that's because of the positive charge on oxygen as a result of this protonation step. So the nucleophile now, which is simply water, the conjugate base of the hydronium ion, will now come and open the epoxide. But you see, this epoxide is on a ring, yeah, so if it is now drawn up, it can be drawn down. If it is up and water will come in order to open it, and water will attack either this carbon and that carbon, there's absolutely no difference between them. The attack of water or the attack of the nucleophile will always be from the opposite side. So if the epoxide is up, water will come from below. If the epoxide is down, water will come from the top. So it's a backside or opposite side attack of water on this protonated epoxide on a cycle. So water will now come, it will attack the epoxide from the opposite side, and this HO bond will then break. This intermediate will be obtained. So we have now a hydroxyl group that has gone up. The water came from below, opposite side, attack. Oxygen still has a positive charge, and now another hydronium ion, another water molecule will come, not hydronium ion, another water molecule will come and take off one of these hydrogens here, so maybe that one, and this hydrogen oxygen bond will break, releasing electrons to the positively charged oxygen. This will generate the trans 1,2-diol and release the hydronium ion as a catalyst, by the way, as an acid catalyst. So it's actually this plus H3O plus H3O plus regenerated, because it could be then used as a catalyst. So this is a mechanism for the ring opening of that epoxide to give the corresponding trans 1,2-diol. What if a cis 1,2-diol is obtained? So in other words, what if cyclohexene now is needed in order to make a cis 1,2-diol from it rather than trans 1,2-diol. Yeah, so the cis 1,2-diol is needed from an alkene. Then the conditions will be different, and those conditions will be a reaction with osmium tetroxide, OSO4, in a first step. In step 2 will be a reaction with sodium hydrogen sulfide and water. So these are the conditions for the osmium tetroxide dihydroxylation of alkenes to make cis diols. Yeah? So remember, this is a cis, that is trans, yeah? Cis 1,2-diol. This is cis 1,2-diol that is obtained from an alkene if the alkene is treated with osmium tetroxide. But osmium, in this case, by the way, osmium tetroxide in this case is used in stoichiometric amount. Osmium tetroxide in this case is used in stoichiometric amount, which means if 1 mole of the alkene is used, then at least 1 mole of osmium tetroxide is used. It's usually in excess, yeah. So this is used in stoichiometric amount based on the balanced stoichiometry, obviously balanced chemical equation, yeah. Okay, but osmium is toxic and it is also expensive. Osmium is toxic, it is also expensive. Toxic and expensive, so this is not very productive in the lab. It's not environmentally friendly because it's expensive, and also then we have to deal with toxic osmium waste at the end of the reaction, and especially if the reaction is carried out or conducted at a large scale. So that's why scientists develop now, instead of the stoichiometric osmium tetroxide, but now catalytic osmium tetroxide method. So instead of using osmium tetroxide in stoichiometric amounts, so osmium tetroxide is used in catalytic amounts. But then if it's used in catalytic amount, an oxidant has to be used also with it. So in order to reoxidize osmium back to the original oxidation state. So another version of this, if you like, to go from the cyclohexene or alkene in general to the cis-1,2-diol is to use catalytic osmium tetroxide and an oxidant such as NMO. An oxidant such as an NMO, and the idea for the oxidant is to reoxidize osmium back to the original oxidation state. If 0.01 mole of osmium tetroxide is used, then it will react with 0.01 mole of cyclohexene in this case to produce 0.01 mole of the product, but then 0.99 mole of the cyclohexene will remain unreacted. So unless there is an oxidant, the reaction will stop there. So this oxidant, NMO, will reoxidize the reduced osmium back to the original oxidation state in order for osmium tetroxide to oxidize another 0.01 mole of the alkene. So that's the idea of the use of oxidants. So this is a method to make cis-1,2-diols from cyclic alkenes, and the ring opening of epoxides will lead to trans-1,2-diols if the epoxide is formed from a cyclic alkene. So if we go back to the formation of the epoxide once again, this is a direct method, by the way, but there is another method which is indirect, and that is to form halohydrin first. So this is the structure of a halohydrin. Okay, that's obtained. So halohydrins are obtained if the alkene is treated with X2 and H2O. This is the halohydrin. If you remember halohydrin formation reactions that we talked about a while ago. So and then halohydrin can undergo reaction with a base such as sodium hydroxide to get the corresponding epoxide. This is another method for the formation of epoxides, but this method this route consists of 2 steps. Yeah, the MCBBA route consists of only 1 step. So of course the MCBBA route is better because it's a 1-step, it's a direct method for the conversion of alkenes into epoxides. So to conclude this lecture on the reactions of alkenes can undergo epoxidation reactions if they react with a peroxy reagents such as MCBBA. MCBBA stands for metachloroperoxybenzoic acid. The resultant epoxides are very important compounds in organic synthesis because they can undergo ring opening as shown in that example. But if a cyclic alkene is used as in cyclohexene and then it gets converted into a cyclic epoxide, ring opening of the corresponding epoxide by the hydronyl will result in a trans-1,2-diol. If cis-1,2-diols are required or needed, then direct dihydroxylation method with osmium tetroxide is used. There are 2 versions of the osmium tetroxide method. the stoichiometric method and the catalytic method. The catalytic method, of course, is a green method in general. This method is better environmentally, it's more environmentally friendly, it is environmentally benign, and therefore this is a green version, if you like, of the osmium tetroxide dihydroxylation. Alkenes can undergo epoxidation and also dihydroxylation reactions.